Hi, everyone. Welcome. My name is Diana Sinton. I'm a senior research fellow at the University Consortium for Geographic Information Science, and I'm really pleased to invite you to our first webinar of the 2023 season. Today, our topic is going to be a portfolio risk analysis of aging U.S. dams in a changing climate. We'll start the webinar formally in just another minute or so as people are continuing to join, but just a few reminders. The webinar is being recorded, and shortly within a few days, you'll get a link to it in your email. As audience members in a Zoom webinar, your audio and your video are unavailable, but we have a Q&A space that you'll see there at the bottom of the screen. If you have questions for any of the multiple presenters, please type them in at any point into the Q&A. We will have time at the conclusion of the webinar to be able to answer those questions, and we'll keep track of them. So if we run out of time to answer your questions, we'll follow up with you afterwards. Those are the main logistics. We'll ask the presenters themselves. We'll be able to hear briefly about them as we begin. Let's see, let's give it another few seconds here to join. So just reminders, this is being recorded and you'll be able to access the link later. You don't have audio or video for this webinar event, but please write into the Q&A space if you need, if you'd like to ask any of us a question. This is a webinar from iGuide. iGuide is the Institute for Geospatial Understanding through an Integrative Discovery Environment. It's an institute funded through the National Science Foundation's Harnessing the Big Idea initiative. Harnessing the data revolution. That's what it is, HDR, Harnessing the Data Revolution idea. And we're excited to share with you our activities around analyzing the aging US dam infrastructure. So let's get started. If we could just advance to the next slide. Our team members from iGuide span a number of different institutions. All of the work you're going to see is contributed to by this large group representative from iGuide. The individual presenters that you'll hear from in the next hour are indicated in bold font here. And with that, I'm going to turn this over to our lead presenter, Dr. Manu Lal from Columbia University. Manu?
Thanks very much, Diana. Okay, there we go. Thanks very much, Diana. It's a pleasure to come to talk to this group. And this one thing I'll mention right off the bat is that this project is actually led by Xiaowen Wang from University of Illinois, who will be talking a little bit later. The particular topic, this is one of the topics in the overall project, and it focuses on dams. And the question is why. We have around 92,000 dams in the US that were built starting sometime in the 19th century. And so they're pretty old. And the question today is, given that these dams are on average over their ages beyond their original design life on average, what is it that we are looking at in terms of potential risks or needs to refurbish these dams across the country? The picture that you are looking at is a map of the dams in the United States rated as high hazard, significant hazard, or low hazard. And that does not mean that they are likely to fail. That's a rating which indicates whether or not there's likely to be loss of property or life if a particular dam fails. And so what you see is that across much of the country, you are looking at high or significant hazard associated with these dams. The challenge we face is that many of these high hazard dams, as you see in the bottom right, are in need of remediation. And we actually don't know the status of most of the dams in the country. That's even more concerning. And most of the dams in the country are owned by private owners rather than by the federal government, which is what sometimes people think about. And so if you see the pie chart in the bottom, it's almost 70% private ownership and almost 20% local ownership. And local means communities, and often many of these communities are fairly small. And the concern is that most of these groups have not had the financial capital to properly maintain these dams. And so they become a concern. Okay, so just to get a couple more setup points across in terms of the kind of risks that we are faced with, these are two maps, one of water supply dams across the US and one of flood control dams. And the dams that have been selected here are dams that are not owned by the federal government. And essentially what we see from this inventory, from the National Inventory of Dams, is that nearly 2/3 of these dams are rated as being in poor, unsatisfactory condition, or we simply don't have a rating, so we don't know. And in general, if one of these dams were to fail, we don't really know what would happen. So that's kind of the concern. And as this graphic shows, most of these dams are in that situation. So this is motivating us to start thinking about, wow, what is really the hazard that we face if this legacy infrastructure were to start failing? Now, what has been happening with dams is that over the last 30 years or so, the dominant storyline in the United States has been an environmental storyline, which is these dams are not necessarily serving their original function. They are harming the environment. There's contaminated sediments that have accumulated behind them. They prevent fish from going through, and they contribute to greenhouse gas emissions. Also, globally, in terms of building new dams, the story has been that arguments have been made that historically these large dams that have been built have not really delivered on the financial returns or the benefits that they were promised. That attitude has been changing a little bit in the last 5 years, driven primarily by climate change concerns, which point to more needs for storage to deal with floods and droughts, and needs for pump storage hydro energy to provide essentially a battery associated with solar and wind energy, which are highly variable, and chemical batteries are much more expensive and environmentally damaging than what would come from hydro. Also, the concern that has been emerging is there are many endangered species, and if low flows were to go to zero, for example, in a river basin, then the concern would be that those species would indeed vanish. And so dams to regulate flow for environmental purposes may also be an interest. So what I'm trying to signal here is that we have risks from aging dams that could be failing. At the same time, there is now a renewal of interest in those storage options for different reasons. And we need to understand both of these aspects from the benefits to society and the risks to society. So the framing that we are looking at in looking at 92,000 dams in the country is this is a large legacy infrastructure. The investment in maintaining this has not been there. There's possibility need for new investments. How do we take this legacy infrastructure, either de-risk it or repurpose it, recognizing all the different uncertainties that are there associated with that? So today's talks will actually focus on a subset of those questions, because ultimately we are interested in possibly an investment analysis. But before we get to that, we have to understand some of the setting. So the questions are shown here on the left, and some of the analyses that will be presented to you are shown on the right. So the first question is, what aspects of changing climate are changing the risk of dam failure across the country? And the corresponding data analysis product that you'll be looking at are what are some of the trends in rainfall or stream flow extremes that change the risk of overtopping of dams, which is one of the major mechanisms of failure. Second question on the left is, what would be the short and long run impacts if a dam were to fail? And remember, there are 92,000 dams across the country, and we want to be able to say something about all of them. So what we are looking at are ways by which we could predict the inundation if a dam breaks and there's a flood wave from every one of these dams. people may or may not appreciate this, but some of the largest losses of life that have happened from flooding in the United States have been from dam breaks. So that's the context that we are trying to establish here. Third is, given a finite budget, what's the best time schedule for investments in the nation's dams? That's the driving question there. And there's preliminary analyses which we are focusing on in today's talk, which are what are the critical infrastructure elements, populations, services, and ecosystems that would be impacted in the short and long run? What are the economics associated with it? And what are the meta-coupling from the place of failure to the rest of the country in terms of supply chain impacts or other factors? Once we have that, we can start looking at portfolio risk optimization under uncertainty, but that's not something we are talking about today, unfortunately. Okay, so just to set this up, the things we are looking at are climate risks that drive failure of a dam through overtopping, and what those map to are changing probabilities of extreme rainfall and rainfall that has occurred prior to that extreme event, because those influence the probability of having the reservoir be full and then overtop and leading to inundation flows. That drives us to downstream inundation if a dam were to fail. What's the areal extent of that? What's the depth of that, which would then lead to impacts? And we are trying to understand that using a physics-based model called HECRAS, but it's expensive to implement this model and it's time-consuming. So what we are trying to do is do an automatic application of this model and then use machine learning tools to actually answer the question of what would be inundated at any of the places that we would be interested in. That leads us into methods by which we can do network analysis on if when the downstream flood wave is generated at any of the 92,000 locations, what would be the different impacts associated with those short and long run. And this is using a variety of tools such as GIS, network analysis, and economic models. That leads us to the last piece, which is, okay, once we understand the risks and what are the governance tools that are available and mechanisms and bottlenecks that are needed to understand what kind of resilience can be engendered by interacting with stakeholders. And that is the geospatial knowledge hypercube, is the tool that's being developed in that particular context, and you'll be hearing about that. So let's start with the first question, which is the climate question. And typically, the background on this is that when you talk to the engineering community, they say it's very unlikely that a dam would fail because of overtopping, because we design spillways for very extreme events, like the 10,000-year event. However, the way reservoirs are operated is that the concern for drought motivates the reservoir operator to keep the reservoir full most of the time. So if they have filled the reservoir because there was a general wet period and they want to keep the water around, and then an extreme storm event happens, you could possibly get overtopping. So the two questions that you'll hear about are, did dams that failed recently or had some kind of hydroclimatic failure, did they really experience a very extreme rainfall or flood event, or was it a modest event following a wet period? And then if that is indeed the case, how are the risks of these kind of failures increasing over the last century? So you'll hear from two speakers on this question. And the first one is Jiangwu Huang from North Carolina State University. So I'm passing this on.
Thank you, Dr. Law. Yeah, so many cases of recent dam failures were attributed not only to a one-day extreme rainfall event, but also to extremely wet conditions preceding the failures. For example, during the Oroville Dam failure that happened in 2017 in California, the rainfall event at the day of the incident was not that extreme. It was rather quite moderate, but the high antecedent precipitation that happened prior to the event saturated the basin and filled up the reservoir and eventually promoted overtopping of the dam. So we started wondering what the climate was like during the actual hydrologic dam failures that happened in recent years. To solve this question, we employed the ASDSO dam failure dataset and focused on 569 dam incidents that happened due to hydrologic factors since year 2000. The figure on the left shows the map of the incidents, and the bottom shows the number of incidents per year. Yeah. So and we looked into the one-day rainfall that happened during the incident and the antecedent witness prior to that. Here, the one-day rainfall that happened during the incident is denoted as A star, and the antecedent witness that was given prior to the incident is denoted as K star. We determined the return period of A stars and K stars, and also their joint occurrences based on a statistical model. And it turned out that the one-day rainfall during these dam incidents were actually quite common. The median return period of A star, it's A star actually. A star was estimated as around 4 years, but K star was quite rare, showing a median return period of 29 years. The median return period of their joint occurrences of A star and K star was estimated as 52 years. So if we take an example from one of the most recent dam failures, which is the Edenville dam failure that happened in 2020, the one-day precipitation during the incident was estimated as a 8.5 year event, and the antecedent witness was estimated as the 21-year event. The combination of those two was a 181-year event. The maps on the right, they show, oh, sorry. Yeah, the maps on the right show the probability of daily rainfall exceeding the A star. The top right figure shows the probability of antecedent witness exceeding the K star, and the bottom left figure shows their joint exceedances. In overall, except some areas in the northeastern and the state of Carolinas, the maps indicate that most of these dams can easily have daily rainfall greater than that happened during the incident, while the antecedent witness and their joint occurrences were quite rare. Yeah. After looking into the dam incidents individually, we aimed to investigate whether there are statistically significant trends in the climate signal that may amplify the risk of aging dam failures. We have more than 90,000 dams across the nation, and most of the dams are now more than 50 years old. And many of these dams are even evaluated to be high hazard dams, implying a high level of threat if they fail. So it would be critical to explore whether the changing climate is posing a high risk for overtopping of these aging dams. For this exploration, we use the CPC daily precipitation dataset that provides a gridded time series of precipitation at the 0.5 degree spatial scale level for a period from 1979 to the present. And similarly to what we have done in the works from the previous slides, we look into the annual one-day extreme rainfall, denoting them as A, and the antecedent witness prior to the date of A, denoting them as K. Well, the model is not showing up here in the slide, but A was modeled based on a non-stationary GEV model, and K was modeled using a 2-parameter gamma distribution. And their non-stationarity was modeled with a linear trend term in the location and the scale parameters. The bivariate model of A and K was developed using a stationary copula function. Based on the developed models, univariate extremes of A and K were explored in terms of their 10-year and 100-year return levels. Here we're looking at how the 10-year and 100-year events of A and K have changed over time. The red colors indicate increases in the magnitude of them, and blue colors indicate a decrease. For A, the changes in the 10-year event and 100-year event show similar spatial patterns to each other, mostly increasing across the contiguous United States. Meanwhile, the 10-year and 100-year return levels of K have changed significantly as well, and both consist of spatial patterns with an irregular mixture of positive and negative trends. Based on the fitted bivariate model, we were able to find regions where the probability of joint exceedances of A and K are significantly changing. The probability of A exceeding its 100-year event following K exceeding its 10-year event has been increasing in the northeastern region. Also California, Washington, Colorado, and in many other regions across the contiguous United States. One may notice the high spatial variability of the map, which is attributable to the pixel by pixel analysis. So the next presenter, Adam, has investigated the spatial continuity in these trends. It's all yours, Adam.
Hi, everyone. John, could you help me change the slides for me, please? Because I don't have the link to do that on my side anymore. So yeah, with our analysis, the data set that we're using is similar to John Woo's. It's at a lower resolution, though. It's at a 1 by 1 degree resolution. And this data set allows us to examine a longer time period. So specifically, we're looking at the years between 1950 and 2015. So what we first do is come up with counts for the number of extreme precipitation events per year at each location within our data set. So for each location, we use a location-specific threshold for creating these counts. We do the same for the preceding precipitation. So we're looking at the 30-day preceding precipitation for this second set of counts, and that's done using 95th percentiles. And finally, we have a combination of these two sets of count data, where we're saying that for our flood risk counts, we're looking at the number of days at each location per year where extreme precipitation occurs alongside the heavy preceding precipitation. So these counts that we're looking at in bold, those refer to when both thresholds are exceeded simultaneously. Could we see the next slide, please? Thanks. So when we have this count data, essentially that means that we've got a set of points in 3D space as indicated on the right. So we've got longitude, latitude, and year as the dimensions. So when we have this set of points in 3D space, we can view this as a Poisson point process. So what we're assuming here is that in a small local region, the number of points there is distributed Poisson with parameter lambda. So the goal here of our analysis is to estimate a function for lambda. So the function that the form of the function that we're using for lambda is indicated in bold again. So it's a function of longitude, latitude, and year, and it's a linear function. So this is similar to linear regression, except that we're assuming Poisson errors rather than normal errors, and also beta 3, that's a spatially varying coefficient. So beta 3 is actually a function of longitude and latitude. And to fit this function for beta 3, we're using 2D splines. So if we fitted this model to log lambda rather than lambda directly, that would be a Poisson regression model. But that doesn't really allow us to capture the linear trends in the data, and also makes interpretation of the model a bit more difficult too. So here we're just fitting our linear model to lambda directly and assuming Poisson errors. So this is the setup for our Poisson process model. Next slide, please. So when we look at the actual results that we get, so specifically the estimates for beta 3, so this is what we're most interested in because it gives us an indication for the increase in flood risk across the time period that we studied. We see that the coefficients, those are all positive across the study domain. And if we interpret those coefficients as a percentage increase in the flood risk across the study period, that corresponds to roughly a 100% increase in flood risk. So this is quite different from the approximate percentage increase in extreme precipitation counts, which is on the magnitude of around 50%. So we've seen a greater increase in the flood risk across the study domain. And there's also a different variation in how that coefficient differs between different regions. So, and these coefficient values that we estimate are also statistically significant across most of the study domain too. So on the right-hand side of this slide, that top right plot, that indicates the lower bounds of 95% confidence intervals for this spatially varying coefficient. So it is statistically significant across most parts of the United States, but specifically our results are statistically significant at the regions of the United States where we've estimated the highest increasing trend in flood risk. And if we look at the lower right plot, which indicates the upper bounds for those 95% confidence intervals, we can see that at the top range, there is quite high there are quite high estimates for that at the regions where we have estimated the highest increase in flood risk across the study period. So next slide, please. So if we compare what we have here with Zhongwu's results, I think there is some correspondence between the two. So for example, if we look at the lower left part of the plot corresponding to California, in my analysis here, we've seen the highest increase in flood risk, and that was also similar to the results that Zhongwu has achieved. So yeah, that's a summary of the results from my side, and now I'll pass on to the next speaker.
Okay, so I think we just had a summary of the two presentations. Is that basically we identify a high daily rainfall and a high rainfall in the preceding 5 or 30 days as a proxy for the hydrologic dam failures, and that if you look at both of those events together, happening together, that's where the risk is going up in the most dramatic way, and we need to understand that. However, as you look at different periods of record, the magnitude of these trends varies, which suggests that interannual and decadal variability of climate is also important in different regions and needs to be understood. So in the future, we'll be looking at that as well as future climate projections associated with climate change, and try to refine these risk projections so that in a time-structured way, we can understand what may be the implications for different parts of the country. The next part is this question on, okay, so let's say that we've identified that a particular dam has failed. In this case, what would be the way to understand what is the impact of that in terms of what areas get inundated? So Cyan Day is going to talk about this.
Hey everyone. So so far we have talked about the cause of dam failure, which is the rainfall, the weather. And the next is now the effect, which is that if the dam fails, what happens? Well, obviously there's catastrophic flooding. And to be able to be ready for that, what we need is information regarding flooding, both static, as in what are the areas that are getting flooded, and dynamic, as in which areas are going to get flooded when. And all this kind of information is critical to be able to plan for the future, to have mitigation measures in place, and also to estimate vulnerability so that we can allow long-term planning as well. Now, while it is important, there are some huge challenges with modeling the floods related to dam failure. First and foremost, well, there are just too many dams. There are 900,000 of them, and there is no way we can individually model each one of them. Second is that it's extremely data intensive. You need a lot of different kind of data, some of which are available, but some of which are not, such as the reservoir bathymetry and what are the hydraulic structures that are available around. And finally, although this is hydrodynamic modeling, this is separate or different from, say, river flooding, where you have this huge flood wave going through, which kind of breaks many of the assumptions that we do for standard river flooding scenarios. So there are quite a few challenges associated with this. And when we started solving these, the first assumption that we take was that we are going to solve for the worst case scenario, which is we'll assume that the reservoir is full, and then there's a sudden and complete failure of the dams. So first, what we did with this is that, so the first thing that we did was we tried the software called DSS-WISE. It's developed and maintained by the University of Mississippi, and it's operated for FEMA. They have a really nice system where they already connect to the dams in NID and also get relevant information automatically from different sources of data. They do require some user inputs, but once you give those into their portal, they try to create a simplistic 2D hydrodynamic model. And they are run in their own servers, and they finally give you information regarding, say, the inundation maps, the time of arrival, and even human consequences analysis if required. Of course, it's a web portal and it cannot be automated. So a user has to have an account and be able to log in and work on all of those things. We did run a few dams with this software. And on the left-hand side, I'm showing you the Folsom Dam, which is uphill of the city of Sacramento. It's a huge dam. So imagine if like there's a 275 feet water wave coming through down the hill and there's a flat valley. It's going to pretty much flood the entire Sacramento if it breaks all of a sudden. And the model was actually able to reflect all of that. On the right-hand side, I'm showing you the El Vado Dam, which has a very narrow and confined channel that's leading into the dam. So what happens is that even if the dam breaks, there is not a lot of flooding in the vicinity. But what happens is that the flood wave goes and hits the reservoir downstream of another dam, and then that gets flooded, and that leads to flooding in the vicinity of that dam. And this is also something, this kind of coupling effect is something that DSS-WISE was able to capture and show us in its inundation extents and other outputs. So these kind of areas where we're modeling the individual dams is something where we are going by DSS-WISE, and these outputs are being used by the resilience research team, which you'll hear in a bit. But our overarching goal still remains getting to somehow find the vulnerability for those 900,000 dams. And DSS-WISE unfortunately cannot do that in its current state. So we tried to come up with our own framework, and that was to create simplistic HEC-RAS models where we can model as many dams as possible. Obviously, we can't probably go to 900,000, but even if you can go to 500 or say 1,000 and have a representative data set, we can then use AI ML to sort of come in and take those data to be able to interpolate or extrapolate those results to other dams as well. So what we do is that we start with a dam from the National Inventory of Dams. And from there, we try to figure out what are the dam location, what are the model extents, what kind of dam it is, so that we can make some assumptions regarding the breach parameters. And we then connect to different databases, such as the NAD, the NHG, or the NLCD. We get data from that, post-process everything so that we can create files in HEC-RAS using Python. And that allows us to pretty much create our own HEC-RAS models. And once we have HEC-RAS models, we have another framework that can take those models and run them and create extents or any other output that you want. So essentially, it's like a data acquisition, data model creation, and model simulation. The entire thing is supposed to be automated with Python frameworks. We have automated the data acquisition part and the model simulation part completely. And the model creation part is currently a work in progress, but we have made some progress on that as well. Now, once we have those models, another thing is that we need to know if they're producing good results. So we need good validation. But considering the worst case scenarios that we are seeing, there aren't a lot of real life data out there for this kind of situation. So in addition to validating with whatever data we have, what we are going to do is do an uncertainty analysis to be sure that what we are producing is not only right, it's relatively more accurate. And in that case, we can also come up with confidence bounds. Again, we have control over our model, so we can run them as many times as we want. So we can do something of a Bayesian analysis or a Monte Carlo simulation to provide probabilistic maps as well. I'm showing you one demonstration of the El Vado Dam. So on the left-hand side, we have this automatic data, the DEM and the land use from our Python frameworks. In the middle, we have model creation. We took the NSG lines. We created some simplistic 1D HEC cross sections. And then we ran them currently with 1D steady, which I know may or may not be accurate, but it was matching pretty well with the DSS-wise results. And currently, we are trying to ensure that we can sort of expand this from 1D steady to 1D unsteady, and then eventually to 2D models as well. So that was all about how to get the flooding. But the thing is that flooding itself needs context. Not all areas are equal. And for that, we need to evaluate the vulnerability. And for that, I hand over the presentation to Jinwoo for this next part of the presentation.
So, yeah, there are two parts to this, and I think Jinwoo is going to talk about how one can identify what kind of impacts would the dam failure inundation have using network properties. And then the other question here is on short and long-term economic impacts. And that we won't be talking about today as such, but we can discuss that maybe in the Q&A.
Okay, so the research I'm conducting is the impacts on the dam failures on the population. And so our research question here is, what are the characteristics of population who are vulnerable to the dam failures? And as a preliminary analysis, we are looking at the 427 federal dams in the contiguous United States. And then this is the third step of our entire projects, just to remind your follow-up. Okay, so for this particular analysis, we employ the 3 steps. So the first step is to identify which census block is flooded or not from a particular dam failures. And the second step is we employ 2 spatial analysis, spatial correlation. The first thing is bivariate Moran-I, and the second is bivariate local Moran-I. So the bivariate Moran-I is a global index. So it computes the correlation between the census data and the flooded information. And for the bivariate local Moran-I, it's gonna show us the local clusters, whether it has the higher social vulnerability of the census data, and also there's a high risk of the flooding. And for the third step, we cluster the dam based on the Moran-I index of each dams. So in this part, we employed the 17 census data so far, and we are grouping into the few small groups, whether to investigate which group of the dams has the impact of the socioeconomically disadvantaged populations. So in addition to our research workflow, I'd like to highlight the computational platform we used. So since we are scaling up the analysis for the national level, there's a very significant computational intensity. So we are using the combination of CyberJet compute and the HPC. So for the HPC, we are using the brand new high performance computing resources called Anvil, which is located at Purdue University. And also we are employing the CyberJet compute as a middleware talking to the local and the remote environment. And in addition to this computing platform, we also modularize our analysis into a few steps. We modularize our few steps of analysis into one. This is because we are conducting this analysis in a very big groups so that we can meet these if our module meet the FAIR principles, we can increase the reproducibility and replicability of analysis so that our other members or our team members can easily adapt this analysis for their own study. Okay, so let me dive into the result. So this is the dam. So the dam called J-Strom Thunderbone Dam is located in the Augusta, Georgia. And according to the National Inventory of Dams, if this dam fails, it's going to have an impact on 53,000 population. And also it's going to have the economic impact over $4 billion. So which is very significant. So if this dam fails, though, the impact on the population are shown on the right-hand side. So again, this is the local clusters between the local spatial correlation between the census data and the dam flooding event. So the red color HH cluster means that there's an increased vulnerability, like there is an increased social vulnerability, as well as this area has a high likelihood to be impacted from the dam failures. So for example, of the mobile home, you will see the red clusters along the river, Savannah River here. So they are very highly correlated in this area. And in addition, another variable called the population age over 65 years old, we can see the two hotspots near the Augusta, Georgia and the Savannah, Georgia. So those are the location has an increased risk. So by combining this result into the national level, we can cluster the dams into 3 groups. So the first group A is the dam impacting on the socio-economically disadvantaged population, and the cluster B is random result. So it can neither have an impact on disadvantaged population nor the advantaged population. And the cluster C is a mixture. So it has the impacts on there are more residents about the mobile home residents and also the elderly people. But for other variables, they have a less correlation coefficient resulted in this cluster C. So our focus here is the dams who are impacting on the socio-economically disadvantaged population, because they are less resilient to the natural hazards and disasters. And their locations are mainly in California, Colorado, New Mexico, and New Hampshire area. And then, so this is one example of our knowledge discovery from the GIS side. And the next slide, Xiao and Wang will talk about the geospatial hypercube.
Thanks very much, Jingnu. See if I could get you the request to have control of the slides. Anyway, I'll start speaking. You've learned so far our statistical modeling approaches to analyzing the risks of dam failures in the climate change context, but also you've learned our mechanistic modeling approach to understanding flood inundation distribution. And you learned just from Jingnu understanding the impact of potentially failed dams on populations, especially vulnerable populations. So for this part, the data is highly unstructured, different from the data sources you've just learned are mostly structured data. For massive text data, here we're interested in sifting through tons of news articles, literature, to see, for instance, how the dam failures are discussed in papers and in newspapers and in social media. This source of data is unstructured, it's massive, sometimes noisy, but it has rich information, especially related to the impact of dam failures or potential failures of dams. And then if we could get this data harnessed, we have tremendous opportunities analyzing such data in our downstream tasks, which I'll show you using an example. So here, the example is a particular text content discussing some residents in this area evacuated to high school after dam failure threatens a city. This is in 2020. And if we take this data using AI machine learning models to transform this unstructured data into a cube, this is a multi-level cubical structure on the right side of the slide. You see, for instance, the dams, specific IDs, and also the years as these dams are evolving, as well as the dimensions of impacts of potential dam failures. So this cell example there, cube has all these different dimensions to plug the text data on the left side into this cubical structure. So you might heard about ChatGPT, which is actually built on similar AI technologies as our approach. Actually, we started our work before ChatGPT became popular last fall. So if I would ask questions to ChatGPT, given the news article content, the link is there, posting the question like, what dam failed, what causes the dam to fail, and what are the impacts of the dam failure. So based on the output of ChatGPT, you could see the information on this table, particularly near the dam site, discussing this dam failure, from the effects of the failure to the flows of people information. In this case, is people primarily, and also agents associated, meaning who are impacted. There's really no specific discussion of the causes that ChatGPT could uncover from the Q&A process. We experimented, but now you see the potential of doing this natural language processing, sifting through massive text data. You could uncover or reveal the causes, effects, flows, and agents associated. So this different aspect of understanding dam failures is part of our meta-coupling framework, initially developed by Jack Liu, a team member within iGuide. So the idea of this framework is really to understand coupled human natural systems as a multi-scale complex systems of social, economic, environmental dynamics, not only at the local level, but also adjacent to the local level, as was from the distant locations that are connected to the local and the regional dynamics. So now if we put this meta-coupling framework into the context of sifting through harnessing the text data, and we could see from the causes, effects, the flows, and the agents associated, and also in the different roles here is geographically at the location of dam failures and near the location of the failure, as well as far away from the dam site. So our goal is to be able to fill this table, using ChatGPT as a test. It's not currently able to get all these parts filled into this table, but our approach is to augment this AI approach to rigorous social science to be able to understand this network of stakeholders and communities to better understand the resilience of populations to dam failures. So for that component, I'm transitioning this presentation to our colleagues at Utah State. In particular, Bailey is going to tell you how we conduct our social science at the community level. Bailey.
Thank you, Xiaowen. Okay, let me take control. So like Xiaowen mentioned, we are interested in looking at the interaction of downstream stakeholders and diverse interests of these aging dams. So we're looking at assessing those interactions. We're also wanting to assess how do local perspectives and knowledge differ from information that's available around these aging dams. There we go. So if we look at the recent case study that was mentioned earlier of the Edenville Dam failure in Michigan, if you look at the response report, they say that relationships and collaborative planning before an incident greatly impact effective communication, coordination, and response during an emergency incident. So we can see that these collaborations and relationships that are built before anything happens create trust and create confidence within various individuals, entities, and agencies, so that when a disaster does strike, people can react accordingly and in a more efficient manner. So what we're looking to do is we are looking to assess these interactions all the way from no interaction all the way up to collaboration by doing various case study interviews. We're currently looking at El Vado Dam that I believe Cyan mentioned, which is in northern New Mexico. We want to identify some vulnerabilities in the inundation zone, so like critical infrastructure, sensitive ecosystems, vulnerable populations, and then talk to some key informants, so stakeholders, diverse interests that are near the dams, people that live near dams, and just get their thoughts and reactions and how much they interact with others around these issues of aging dams. So we'll be doing some participant mapping to capture their knowledge of the spatial vulnerabilities around these aging dams. And I know we don't have very much time, so I'll wrap it up there and I'll pass it along to Manu to wrap us all up so we have time for questions.
Okay, great. Thanks everyone for their presentations. As I said in the beginning, we are at an early stage with this project, and it's a sub-project of a much larger project. Our initial results suggest that there is a way to try to leverage all the tools that we've kind of exposed to develop a set of integrated analyses that we'll share publicly so that local managers, risk managers, as well as water managers and others have access to understanding their context, their risks in their context, as well as allowing national managers such as FEMA and others to understand what the picture looks like across the whole country. So the goal is that we want to be able to provide this kind of methodology that we develop in the US more generally, so that in developing countries or other places as well, people can leverage the tools that are developed here. And as we are early in this game, we are very interested in your comments and collaboration to develop these ideas out. Obviously, there's a lot to be done here, and we have just scratched the surface. Thank you.
All right. Thank you for all of those presentations, our group of panelists. We've got just a few more minutes left till the top of the hour to look at any of the questions that we have. I wanted to just point out for the audience, if you go to your question and answer place on your lower ribbon, you can see questions that have already been posed, and different panelists have responded to those. If you have any follow-up questions to those, please feel free to type them again. We have, if anyone else wants to add another question in there, or if any of the panelists want to respond out loud right now to any of those questions that were there. We have one other, we've got a question here that Jimeng Shi has posed to the group. Manu, you've talked about the HDR approach. If you want to summarize Jimeng's question there and respond to it. Manu, I don't know if you can see the question panel there.
I see it. So the question from Jimeng is about HEC-RAS. Cyan, do you want to talk about that? And then I can pick up and talk about how we can use that to train a better ML model.
Sure. Jimeng, in essence, when we are doing hydrodynamic modeling, we are solving the Saint Venant's equation, but with certain assumptions. So we have the kinematic wave equation, or similar equations based on what assumptions you take or how you simplify the Saint Venant's equation. So we already have models that have complex solvers that are able to iterate and converge to solutions regularly. And instead of creating our own solvers, what we do is we automate the model creation in those software so that they solve the physics equations for us and allow us to take the results out directly. Of course, these models take a lot of time to set up, and sometimes they also take a lot of time to execute as well. So it's a challenge to do it for all 90,000 dams, but we can definitely do it for potentially, say, 500 or maybe even up to 1,000 dams, and then we can move on to the AML part for that.
Okay, so I guess I'll augment that with the ML idea. one of the ways to think about, the output of what Cyan puts out is that it will be an image with different attributes, because it will show the area that has been inundated and the depth to which it has been inundated below a dam. And then the trigger for that is information on the attributes of the dam, how big it was in terms of height, in terms of volume of water behind it, and so forth. So what we are trying to do is to think about ways where we can use techniques that have been developed that do a good job on image recognition and classification conditionally, and use them in a way by which we can extrapolate the results of a well-sampled set of dams that Cyan is going to run with a physics-based model that span the range of conditions that we expect to see across the country. So the idea is that the ML would be working to interpolate across the convex set of those attributes associated with those dams. And then at least we have a very rapid way to estimate what the potential inundation characteristics would be.
Thank you for that, Manu. We have one other question that's been posed about the results of the frequency analysis. Maybe the panelist who has the best response for that could answer. I did want to say, I think it might have been a misspeak that we said there were 900,000 dams. It's actually, so not 900K, it's a little over 91,000. So just want to make sure we bring that down in order of magnitude. We'd be in much more significant challenging situation if we actually had 900,000. So I think somebody might have their hand up, because we're just going to keep microphones off for this. If you've got a question, please feel free to type it out into the question and answer space. And if you, we probably will run out of time to answer all the ones that are there, but if anyone wants to, we have your emails since you registered, so we'll be able to follow up with some responses. Anyone on the group can respond to the frequency analysis questions? Did our research team have a chance to compare the joint exceedance probabilities or return periods with those previous studies?
Yeah.
Go
ahead.
I was just gonna mention quickly that when we were looking at the count data, so we didn't get a chance to look at the counts. We didn't get a chance to look at comparisons for the counts of the joint exceedance events, but for the extreme rainfall events just by themselves, I did do a comparison with what we already have in the literature, and overall the magnitudes of the increases that we see are pretty similar, but there are differences in what we find with the spatial distribution of the magnitude of those increases. But from the literature, it also seems that it's quite common to find differences in the spatial distribution of these magnitudes due to the exact kind of data sets that we use and other sort of parameters like that. And there is, again, also quite a large confidence interval there too. So if we take into account the uncertainty of that, then we do have quite good correspondence in regard to at least the extreme rainfall events themselves.
Super, thanks for that, Adam. All right, we're at the top of the hour. I really want to thank all of the panelists for their thoughtful presentations today. This is an example of how iGuide pursues ideas of convergent science. We have scholars, professors, postdocs, graduate students working together from different disciplines. We've got hydrologists, geologists, statisticians, GI science experts, computer science experts, all working together on complicated issues of, for example, aging dams and other issues of water and food insecurities and things affected by climate change. It takes these multiple perspectives to be able to unravel these complicated problems, and that's what iGuide is working on. So check out our website, iguide.illinois.edu, and you'll be able to learn about other webinars that we'll have coming up, and also frequently offered virtual consulting offices. So hour-long sessions that are a little more informal, and you'll be able to to learn about some of the technical approaches we're taking to these. I want to thank Professor Xiaowen Wang, who's the leader of iGuide, for being part of this presentation today and for steering us all in the important forward direction with iGuide. Thanks everyone very, very much again. And as a reminder, the recording of this will be up on the iGuide website very soon. Thanks, everyone.